Hi everyone, my name is Roland Martinez, and this is a video presentation of my project in Electronics 3 Laboratory, Section E01, under Engineer Ramon G. Garcia, and the project is Oscillator Circuit Design. In this video presentation, I will divide this into three parts, which consists of the design background for the first part, and for the second part will be the manual computation, and for the last part is the LTspice simulation demo. So for the design background, the target resonance frequency is 4.2 kHz, and I will use Wien bridge oscillator as my basis for the design of my oscillator circuit design, and I will use operational amplifier LM471 model, and I will use LTspice for the design and simulation of my oscillator circuit design. And this is the preview of my oscillator circuit design using LTspice. And before proceeding, I will discuss some of the advantages of the Wien bridge oscillator. First, it gives constant output, and different frequency ranges can be obtained by varying the two capacitor values simultaneously, and the perfect sine wave output is possible. It is useful audio frequency range, in example 20 Hz to 100 kHz. And the frequency of oscillations can be easily changed by using a potentiometer. And for the disadvantages using a Wien bridge oscillator, if I chose to use a transistorized amplifier, then more stages are required to obtain a 0-degree phase shift between input and output. And this increases the number of components and cost. And the frequency stability is poor, and it cannot generate very high frequencies. And the maximum frequency output is limited because of amplitude and phase shift characteristics of the amplifier. Next part is the design computation. So before proceeding for the on the design, first is to determine the values for the RC phase shift network, because the RC phase shift network will determine the resonance frequency of the oscillator circuit. First, I need to compute for the value of the R1 and C1, and because R1 and R2 is equal and C1 is equal to C2, this means that the network will have a zero phase shift angle. And we can see that the R1 and C1 is in series, and that is the high pass filter, while the R2 C2 are the low pass filter. So we can say that this RC phase shift network is a band pass filter. So for the manual computation of the resistance on the RC network, I use the resonance frequency formula, which is FR is equal to 1 over 2 pi RC. And my target frequency or resonance frequency is 4200 Hz or 4.2 kHz. And assuming that the capacitor value is, or the capacitance is 3 nanofarads, then I can get the value of my resistance for the R1 and R2. So R is equal to 1 over 2 pi times the target frequency of 4.2 kHz times the assumed value of the capacitance, which is 3 nanofarads, and that is equal to 12.63 kilo ohms. So for the capacitance reactance, or XC, and that is equal to 1 over 2 pi FC, which is the same value as the resistors. R1 and R2, and that is 12.63 kilo ohms. And for the high pass filter or the lag network, the series impedance is equal to square root of R squared plus XC squared, and that results to 17.86 kilo ohms. And for the lead network or the low pass filter, I use the admittance formula, and that is 1 over Z is equal to 1 over square root of 1 over R squared plus 1 over XC squared, and that results to 8.93 kilo ohms. So the phase shift or the phase angle on the lag network can be obtained using theta is equal to arctan of XC over R, and the degree is 45 degrees lagging for the lag network, and for the phase angle for the lead network, and that is theta is equal to arctangent of 1 over XC over 1 over R, and the same value, which is 45 degrees but leading. So the phase angle when these two network converge at the Vin of the op-amp, this results to 0 degrees phase shift, and that is phase angle is equal to angle of the lead minus the angle of the lag, and that is 0 degree. And the other thing to consider is the Barcode Stability criterion, and that is A beta is equal to 1, and the attenuation factor or K factor is equal to 1 over 3. And the voltage gain should be 3 or greater, and the voltage gain formula is AV is equal to V out over V in. Since my oscillator is using a Wien-Bridge oscillator, and that is a non-inverting op-amp, I use the formula for non-inverting op-amp gain, and that is 1 plus RF over R in, and that is equal to or should be equal to 3 or greater. So to compute for the resistances R in and RF, I use the non-inverting voltage gain, and that is 1 plus RF over R in, and should be equal to 3. Therefore, R in is equal to RF over 3 minus 1, and is equal to RF over 2. And considering that the resistances on the inverting input of the op-amp is higher than the resistances on the RC phase shift network. And assuming that the R in is equal to 50 kilo ohms, then the RF is twice the R in, and that is 100 kilo ohms. So to ensure the oscillation or the stability of the oscillation, gain should be higher, and I assume that the gain is greater than 3, and I consider that the voltage gain is 3.1. Therefore, R in is recalculated using the gain 3.1, and that is R in is equal to RF over RF over 3.1 minus 1, and that results to RF over 2.1. And the R in, therefore the R in for the oscillator circuit is 47.62 kilo ohms, and the RF is 100 kilo ohms. Lastly is the LTspice oscillator circuit simulation. You can see on the screen the oscillator circuit design or schematic diagram on the LTspice, and you can see the RC phase shift network on the bottom part of the oscillator circuit schematic diagram, which is consists of C1 and C2 and R1 and R2. And this is the lag network and this is the lead network. The op-amp I use is LM741 model, and for this uh, oscillator circuit design, I use the calculated values on the manual computation, and the resistances are obtained using the manual computation for the RC network, which is for the R1 and R2 is equal to 12.63 kilo ohms, and for the C1 and C2, and that is 3 nanofarads, and for the RN is 47.62 kilo ohms, and for the RF is 100 kilo ohms. This series resistances are the RF or total RF, because the 25 kilo ohms is used to connect with the two diodes 1N4148, which are on opposite polarity. They are connected to the 25 kilo ohms in parallel to stabilize the oscillation of the circuit. So I also use a additional capacitor C3 with 18 picofarads. This capacitor C3 will provide a charging and discharging for the input on the inverting input of the op-amp LM741, and the voltage will be flowing to the RF, and the voltage will flow to the RF and going to the V out, feeding to the RC network, going back to the op-amp. So running the simulation button or the running man on the LTspice and clicking on the output, you can see the generated oscillation sine wave on the plot. To check for the frequency or resonance frequency of the oscillation, we can choose the stabilized wave around at 4.2 milliseconds. We can use the cursors feature of the plot by clicking on the V out, and moving the cursor on the amplitude of the sine wave. Next is adding an additional cursor or cursor 2 to move the another cursor on the next amplitude. We can see that the resonance frequency is equal to 4.18 kilohertz. To make sure that the value we get here in the plot, use the spice directive that measure, and that measure frequency param 1 over T11 minus T10. So additional that measure to get the voltage input or peak-to-peak voltage input, same with the peak-to-peak voltage output, and the voltage gain, same with the VRMS of the voltage input. To check for the values obtained by these spice directives, we can click on the view button or view option and click on spice error log, and that gives the values of the spice directives. And we can see here that the voltage input or peak-to-peak voltage input is 1.76 volts, and for the peak-to-peak voltage output is 5.23 volts, and the voltage gain is 2.99, and the frequency or the resonance frequency is equal to 4192.97 hertz or 4.2 kilohertz. The resonance frequency is equal to the target value of the circuit design. and that is 4.2 kilohertz.